The durability of rover wheels is one of the most critical engineering challenges in Mars exploration. No matter how advanced the cameras, instruments, or autonomous systems become, a rover that can no longer move loses much of its scientific value. Mobility ultimately determines how much of Mars we can explore, and this reality became clear with NASA's Curiosity rover. After more than 14 years on the Martian surface, Curiosity's wheels show severe structural damage. Its aluminum wheel skin contains multiple punctures, cracks, and tears, especially in the thin sections between the traction grousers. The main reason was the unexpected severity of the terrain inside Gale Crater. A major culprit was ventifact rocks sharpened by millions of years of wind erosion. Although Mars has a thin atmosphere, wind carrying fine dust can slowly sandblast exposed rocks into extremely sharp-edged structures. These rocks turned out to be far more destructive than NASA originally predicted. When Curiosity's roughly 900-kilogram mass rolls over these sharp edges, the load gets concentrated into tiny contact points, generating extremely high stress on the wheel surface. Over time, this repeated stress causes plastic deformation and eventually tears the aluminum skin. By the early 2020s, wheel damage became serious enough to affect mission planning. NASA responded by changing its drive strategy. Engineers improved traction control software and began selecting safer routes, even if those routes were longer. Reducing wheel slip and avoiding hazardous terrain helped slow further damage and preserve mobility. Curiosity's damage directly influenced the design of Perseverance. Although both rovers use similar suspension systems, Perseverance's wheels were heavily redesigned. Curiosity uses thinner wheels with fewer, widely spaced traction grousers, leaving larger, unsupported aluminum sections vulnerable to punctures. Perseverance uses a stronger design with 48 curved traction lugs, compared with Curiosity's 24 larger grousers. More lugs distribute mechanical load more evenly and reduce stress concentration. NASA also modified the tread geometry to a tighter zigzag pattern for improved resilience inside Jezero Crater. The wheel structure remains aluminum-based because of strict mass constraints, but thickness distribution and structural curvature were optimized to improve fatigue resistance against jagged basalt and sharp rocks. The objective was not to eliminate damage entirely, because that is unrealistic on Mars. The goal was simply to slow down damage progression. NASA also modified the tread geometry to a tighter zigzag pattern for improved resilience inside Jezero Crater. The wheel structure remains aluminum-based because of strict mass constraints, but thickness distribution and structural curvature were optimized to improve fatigue resistance against jagged basalt and sharp rocks. The objective was not to eliminate damage entirely, because that is unrealistic on Mars. The goal was simply to slow down damage progression. Terrain affects wheel lifespan more than distance alone. Curiosity encountered dangerous regions filled with fractured, sharp rocks that created extreme point loading. Perseverance faces a different challenge inside Jezero Crater, an ancient river delta containing sand, sedimentary rock, and basalt fragments. This mixed terrain creates both abrasion and puncture risk. Loose sand increases wheel slip, causing more abrasion, while rocky terrain increases structural stress and puncture probability. But wheel damage affects more than just wheels. Repeated vibration from rough terrain travels through the entire mobility system, including steering actuators, suspension joints, and structural struts. Over thousands of drive cycles, this cyclic loading contributes to long-term fatigue in mechanical components. The lessons from these damaged wheels are now shaping future Mars missions. Engineers are studying compliant wheels made from advanced materials, such as shape memory alloys. Unlike rigid aluminum wheels, these designs can flex under load and absorb impact energy, reducing stress around sharp rocks. This could dramatically increase rover lifespan. Ultimately, wheel durability determines exploration range. Every crack, puncture, and deformation helps answer one critical question: how far can our robots travel before Mars stops them?